Welcome to the pump up for AP circular motion. I'd like to do a quick review of centripetal force and the equations associated with things moving in a circle. We're going to start here with flat circles. This would be, we're looking at this view from above, you can kind of see here. And if we start with kind of a basic idea here, we'll start with the, let's say the ball over on this side. And the ball, let's say, would be going around some kind of a circular path with a velocity going in this direction. Remember, the velocity is tangent to the path of the object. And then we could start asking some questions about, like, for instance, what's happening with the string. Well, it's fairly straightforward here that the string is going to be applying some kind of force on the object in this direction. In this case, what we call it the force of tension that's acting on the object. And that force of tension is what's keeping this going on its circular path. Now, if we took a look at the velocity, for instance, at two different times, let's just go ahead and zoom in on this little thing. Just before this time when the ball is here, the velocity maybe would be going this way tangent. And you can see, we'll call this, let's say, V1. This over here, V2. It's pretty clear if you look at V1, what had to happen to V1 for it to be equivalent to V2 is there had to be some kind of a change in velocity, that went in this direction. And if there's a change in velocity going in that direction, that actually means that there must also be an acceleration in that direction. So we could say that since this is a force going towards the center, this tension in this case, there must also be an acceleration in that direction. And we're going to call that the centripetal acceleration. Now I'll come back and work out the equations for this ball in just a second, but let's first of all kind of review some big picture things about this circular motion. First of all, you can kind of see here that this big circle has a radius, as I've shown here, of r. Right here. And so if we could start being specific, for instance, about this velocity then. The velocity in this case is the amount of distance that this thing travels, the ball, let's say, around one complete path, divided by the time that it takes. Well, the distance that it travels is simply the circumference of the circle, which is 2 times pi times r. And we give a special name to the time that it takes the ball to take one full cycle, and we give that the name period, or capital T. Period of time to make one cycle. And that's kind of our basic reference for the speed of the object as it goes around a circular path. Now, given in the text, we also have a relationship for the centripetal force, and that's something you can't really derive, but that's given as v squared divided by r. And this I'm going to go ahead and box. This is an equation that is on the equation sheet for the AP Physics B exam. Now, if we come back down to our example of the ball with the string, we can see here in this case, if we were to do a sum of the forces, and essentially every single one of these problems is really a Newton's law problem. What we're going to do is the sum of the forces. And in this case right here, we're going to do the sum of the forces acting on this ball. And in this case right here, the net force acting on the ball is this force of tension that's acting on the ball. And that must be equal to the mass times the acceleration. But the acceleration that the ball is experiencing is a centripetal acceleration. So we can change this with our equation above to be mv squared over r. And that's our basic relationship for circular motion, mv squared over r. Now, we should make a quick mention of the coordinate system that we're using in this case. You can kind of see in this case I've made the force of tension positive and the acceleration positive. They're going in the same direction, as you can see. And there is this convention in working with these problems that makes them much simpler to work is that you use the towards the center, this direction towards the center, as the positive direction. So in this case, we don't care about really left, right, up, down for signs. We care about towards the center or away from the center. And in this case, positive towards the center will make the signs work out on these equations much more sensible for you. All right, so now if we just continue through a couple different examples that you've seen. This was a ball on a string, again on a flat horizontal surface. So this is This would be something like maybe the ball's on a table. There's a hole in the table and it's being swung in a circle. This could also, this same situation could be a, let's say a race car, a car on a track. The car on a track has a velocity in this direction, but to be following this curved path, it must also have a force that is going towards the inside of the curve. And in this case right here, what's providing that force is the friction force between the tires and the road. This allows us to write the relationship for our equation. In this case, for a race car on a track, a flat track, it would be the force of friction, which of course we have a relationship for as well, which is the mu static in this case, I'll come back to that in a second, times the normal force is equal to mv squared over r once again. Now, this is an important point to notice. In this case right here, the type of friction that we're talking about here is static friction, because these tires, even though they are rolling forward, they are not sliding sideways. And that's what we need the tire to do. We need it to stick and not slide sideways. So static friction coefficient, and that's our relationship if it's a car on a flat track. All right, we could also, moving along our examples here, we could have a planet that's orbiting, let's say, a sun at the center of the system. In this case, the velocity would be tangent to the path, something like this would be our velocity vector, but the force vector would be towards the center. And you can imagine what's providing this force is a gravitational force in this case. Now with the gravitational force then, we have a relationship for that. The gravitational force is equal to capital G, which is the universal gravitational constant, times the mass. I'm going to simplify this. Your book just has m1 times m2. In other words, the product of the two masses. I'm going to write it this way because oftentimes in these orbital problems you have one greater mass and one less mass, divided by the distance between the two things squared, something like this. Now if I were to continue to set this up, this would be gmm over r squared is equal to our mv squared over r. Now looking at this relationship here, this is not something you have to memorize, but you can kind of see a pathway here for kind of an interesting side calculation that you can use here. Because of the values that you have on the same side, if this is the mass of the Earth and the mass of the Earth, it could cancel from each side. And you have this radius of the path and the radius of the path, one of those squares goes away. And you can kind of see here that you can develop an equation that solves for the velocity, in this case, of the orbit for any object in orbit. And you will occasionally get questions about this. And just algebraic solution for that gives you this solution. It's the square root of big G, big M over your radius. That's the orbital velocity for anything traveling in a circular path around some kind of a central mass. All right, now the last of our examples here, what we're going to do is, you'll notice in your study of magnetism, electricity and magnetism, you also have this effect on charged particles moving through a magnetic field. So in this case, if I had a velocity vector for this positively charged particle, and I had a magnetic field B that went into the page, as I've shown in this case, I would do my cross product here, my V cross B, and I would get a force in this case that's directed towards the center of the circular path that the charged particle is traveling. And that right there is going to be an F sub B, in other words, a magnetic force that's acting on the particle. This magnetic force then can be written with the actual equations. This magnetic force is equal to charge times its velocity times the strength of the field, that QVB. And this QVB then is going to be equal to my mv squared divided by r, something like that. Now again, you can see in this case that we can do some canceling here because we have the velocity of the charged particle here, and we also have the velocity of the particle here, which would eliminate the square on this side. And now you can see that you have a new relationship that could be used to solve for any of those quantities. Often this one is solved for the radius, for instance, or maybe it's the velocity of a particle that travels in a particular radius, and you can use that relationship. Now this gives us all of the relations associated with flat horizontal circles. And you can see the simplification in this view is you only have one force acting on the object. So when you do your sum of the forces is equal to the mv squared over r, you'll just have one term. Things are a little different though when you move to vertical circles. And so what I'd like to do is kind of zoom in on what we have going on down here. These other type of problems, the rules associated with the problems are exactly the same. But you can kind of see here in this case, gravity plays a role in determining the net force on each of the objects. So if we start on the left thing here, this would be a ball that's swung now in a vertical circle. You can look at each of these points around its path. Let's start at the top. And you can say that at the top of the path, this object is going to have still a tension, so some kind of force of tension acting in this direction towards the center. But you also have acting on the object an mg, in other words, the weight of the object. Something like this. We'll have it, let's say it's going around the path, something like this. So there's its velocity vector, and there's its forces acting on the ball. Now, if we were to do an equation in this case right here, you can kind of see here that we'd have some kind of, using our rule towards the center being positive, we'd have some kind of a force of tension plus the weight, mg, is equal to our mv squared over r. And that's going to be the difference now when we do our sum of the forces, you'll have more than one force. Going around our circle, the velocity vector at this point right here, you can kind of see the weight in this case would be acting down, my mg, and my centripetal force now is only the force of tension. So now I'm back to my original equation where just the force of tension is acting towards the center. So that will equal the mv squared over r in this location and orientation. And if I continue my swing around this way, I've got my velocity here. Now I have my force of tension acting up, but I have the mg acting in this direction. And remember this centripetal kind of coordinate system. So I would have f sub t minus mg now would be equal to my mv squared over r. Or my net force acting on the object. These can be transposed. Sometimes these are, you can kind of see this problem can be set up as a track problem. And so on the right I have the same situation only set up for a cart, like a roller coaster cart. You can kind of see the only thing that would happen here would be this term, right, the force of tension, the force of tension, and the force of tension in this case would be replaced in this example with the normal force, in other words, the force on the cart by the track. So in this case you'd have the mg weight acting down, but then you'd have a normal force acting in this direction. Mg acting this way and a normal force acting this way, and mg acting down and a normal force acting up. And you can kind of see you can generate a very similar looking equations for the sum of the forces on each of these objects. A couple final notes here. Sometimes these problems with the carts on a track can also be written as like a cart on a hill. So you could have this object on the top side of this. In other words, let's say it's going around the outside of this curve with some kind of a velocity in this direction. And then, of course, the normal force just points in the opposite direction. And again, you're going to be using Newton's laws, some kind of equation that said this is the away from the center, so some kind of minus n plus mg equals our mv squared over r for that situation right there. Let's see, two more points real quickly. One is to realize, let's go back to our example here with the with our ball on a string. This ball on a string is often given in the form of a pendulum problem. So keep in mind that a pendulum, for the portion of the arc that it is going back and forth, is actually a ball on a string. So circular motion and kind of what we have here with circular motion is also applicable. Hopefully this helped you with your review for circular motion. I'll give you the kind of the big picture before we leave of both flat and vertical circles. Thanks for joining me.